Okay, thank you everybody for joining us for theme 15. We're just transitioning from one session to another. And today our first speaker will be virtual, so we see how this works technologically, hopefully without any problems. As we're moving in and out of the room, I want to take a minute again to acknowledge the sponsors for this theme, which without their contribution, we could not have done that, bringing people from all over the world pretty much to come and share their knowledge and experience, which is not necessarily core geochemistry in this session. And it is an opportunity for us as a community to expand our horizon, expand our knowledge, and learn something about broader geochemistry that is related to society, to indigenous knowledge, to culture, to conservation, and also to teaching and communication. So with that, I will ask our first speaker, who is virtual, to get started. Ramzi, I will let you can introduce yourself first and then go on. Thank you, Kumu Ramzi.
Aloha. Nice to see you all. I'm Goldschmidt22 my students call me Kumu, but that's only if they're learning something. But it's a pleasure to be here. It's ironic because I'm usually there in Hawaii, but I happen to be traveling and I'm here in Spokane where I'm broadcasting today. So thank you very much for having me. Did you want me to go ahead and start, or were you going to go through all the panelists first?
No, you go ahead.
Okay, great. Thank you. Let me share my screen with you all here. Sorry about that. Nope. All right, I hope you can all see that. Again, my name is Ramzi Tom. I'm the Pacific Islands Leadership Institute Director and Program Coordinator at the Hawaii Pacific University. I also happen to be a cultural sustainability planner with PBR Hawaii and the founder of the Life Enhancement Institute of the Pacific. In each of those roles, the underlying practice is really about aligning cultural principles, values, concepts, and thoughts into contemporary practice, including development, policy making, and the like. Multiple years ago, I was involved in a research project, or at least an effort to help clean up the Alawai Watershed Association, the Alawai watershed itself. And at that time, we began to look at the various relationships to water from a Hawaiian cultural perspective. And so today I'm sharing some of those thoughts, the views and values of, as it relates to water from a Hawaiian, or what I'd like to say, an island worldview. And so when we talk about values and cultural values in Hawaii, I'd like to start off by saying that's really just values that we prioritize. I think values at large are universal and global. But the way we prioritize them is why we call them cultural values. In the case of water, I think we all value water to a certain degree, but we all prioritize them differently, how we get it, how we treat it, how we use it. Several years ago at a conference, Kopuna, an elder, had come from an island for another conference, and we heard her gasp when she saw water in the toilet. She asked why it was doing what it was doing there, because where she comes from, you wouldn't use potable water to wash poop away, as she would say. It's hard to come by. And at that point, I think many of us began to recognize the difference in how the value of that particular resource. What I'd like to do is build on this context. I subscribe to the school of thought that context shapes content. And I shared this image with you because the context of Hawaii, where we are today, where you are, some of you may recall the examples of icebergs. Well, Hawaii is much like that example. So much more of the island is under the water rather than above it. And in this view, we can see that. And this is very much like these principles I'm about to share with you. Oftentimes we just scratch the surface, but they have so much more meaning when it comes to the application and its operationalization of those values. we like to talk about them, but how do we really apply them? And so this afternoon, I'd like to share some of those concepts, the origins, where they come from, and then basically how they apply. This notion of water, both fresh and salt water. In order to really understand it, we look into our origin stories, an ancient genealogical chant that speaks about where we come from. And in this case, that chant is called Kumu Lipo, Kumu the source or resource, Lipo referring to the deep, dark blue space. And when you unpack that, it talks about how everything, life, basically evolved and came out of that ocean, the deep, dark place. Not so different than each of us coming from a lipo, our mother's wombs, that deep, dark liquid. And so it connects us back. We're all related in that way. And the Kumulipo says that the waters, the first waters that all of us come from, is what makes us related. It's what connects us all. So with that in mind, I'd like to open properly by bringing you into this oli, or actually more like a chant. I'll speak it for you so we can get that term out. E holuko no no ke kino amika uhane. He maalama pono kamanao ke ola ke kino I kamana apauloa. Aloha, aloha, aloha. Now in those words, it edifies what I was just talking about, this interconnectedness, this interrelated concept. In the first part of my phrasing that I just shared with you, it says, unify mind, body, and spirit. That is a term for what we call pono, an alignment of not just with yourself, but all things. It also suggests that we're all connected to this source of life, but also to one another. And not just while we're here in this room, but when we do move on and do other things. We are all connected by water, primarily because we all started there. This is the image of Hawaii itself. And when we look at the root words, the concepts and principles behind the language, which is an elemental language, as a cultural practitioner trained by multiple elders, this is one of the foundational thoughts and concepts. The word Hawaii can be broken down into several root spiritual elemental terms. The word Ha, that first word, refers to the life-giving breath, the spiritual air, that space between you and I. And of course, we know that there's water in the atmosphere, the air. So we are actually in water, although it may not feel like that, but that is the moisture that we're feeling in the air. That's the Ha. The second, the Vai, that refers to water, the spiritual waters, the life-giving water. And as I'll show you shortly, it's not just the fresh water, but life-giving water is both fresh and salt. The last concept is E, the letter I. E refers to the creative energy, some might call God, creative energy of the cosmos, creation itself. So therefore, when you put the word together, Hawaii, we're talking about a place by name as actually acknowledging the element of forces of life, of Ha, air, Vai, water, E, spirit and relationship. And so when we explore Hawaii and the concept of water through that lens, the waters then become critical. We're surrounded by that water. It's everywhere. Wherever you look, there's water. We are the most secluded, distant place on the planet when it comes to being an inhabited place. This water starts out in the atmosphere, in the air as clouds. It's captured along the mountainside. Clouds and rain becomes rivers and streams. Those rivers and streams percolate, run off into the ocean, and they become the sea, feed into the sea, and the cycle starts all over again. So from the Vai, freshwater to the ocean, the Kai, begins to explore the dualities, these different energies in water, which actually talks about life at large. So the energies of Ku and Hina, Kane Wahine, masculine and feminine. These two energies are described in the waters themselves. Vai is feminine, while Kai is masculine. Vai is internal, while Kai is external. It speaks about an requirement of looking for balance at all times, while the Vai washes the land and brings things to the ocean. That's salt, those sediments, everything goes into the sea, feminine to masculine. It also speaks about the opposites. And in this case, the consideration of resource versus waste. And when we talk about resource management, there are no waste. There isn't any waste. Someone is always using it, applying it. So when we reframe that, all of a sudden we adopt different practices to utilize that resource more importantly. So this is what most in the Asian culture may consider that yin and yang, that opposite. We also speak about relationship, like you're talking about there, is that what are the relationships and not just the transaction. The island worldview is about relationships, where we come from. We're related to not just the land, our family names are connected to those places, but potentially to the winds, as well as the rains, the waters, and the streams and rivers. They're embodied in our practices of who we are. So when the first arrivals came to the island, to step on the island, they found these rich resources available to them, wetlands and wetlands for farming and agroforesting, all of which was supported by this abundance of water and rain. Those of you who are on geology will recognize this, but the island of Oahu in particular, where you are, is located in such a way that the angle of the mountain themselves and the height of the mountains allow them to catch the easterly trades and the winds and the clouds in such a way that there's an abundance of water. And of course, into our aquifers, into the dike system, which we are now seeing in contemporary time being compromised by some of our development practices or the lack of proper policies to protect those resources. But it's about relationships on land as well as in the sea because of the nearshore impact that we all have. Another concept is that the liquid, this water force, the relationship of hot and cold, fire and water. This is an image by Herb Conning. Can you hear me okay? Yeah. Okay. This is an image by Herb Conning depicting of what it might have looked like when some of the early voyagers came to the islands, is that as the volcano is erupting, this fiery liquid was entering into the sea while they floated across this other cold liquid. So we have a hot and cold experience, fluidity, movement. In Hawaiian, when we use the word vai, we refer to this powerful resource, something of great value, liquidity, fluidity. So it's applying in a contemporary economic way, but it also looks at anything of great value might be referred to as vai or vai. And in this case, when they arrived here, they could definitely see the power of these elements working together. When we speak to the elements of air, water, fire, the utterance of this sound is ah. When you say ah in Hawaiian, you're referring to the fire, heat, God energy of the sun, which of course, like the lava on Earth, is fluid. There's movement. That movement in there is reminiscent of hot water. That is the ah. But the element of water is captured in the sound of E. Now, earlier I told you E was this notion of relationships and the creative energy. Well, E in this case, like the little drop of water you see, is referencing the spirit of water. And when you put these two energies together, Ah and E, fire and water, this combined thought process creates another word called Ai. Ai is the word for food. It is the word for energy. It's what they exchange. Ai is to feed, Ai is to eat, but Ai is actually the noun itself for food. Well, interesting enough, when you put those two elements together, what we're really seeing is this notion of steam, hot and cold, energy created by this. And so this recognition of these two things working together, we get our energy from food. The land continues to produce energy through geothermal, but requiring both elements to be working together, and us, of course, working with it. So the waters are part of everything that we do. It's captured in our legends and the stories. This image captures the picture of two deity, Kane and Kanaloa, and they are said to travel together throughout the land, Kane representing the land, Kanaloa representing the ocean. whenever they got together, it was said that they would then find and create these springs and rivers. So many places you go on the islands will have names for these two deities, these two entities, to acknowledge the stories of where they found these springs for the people to live in. And so this is a continued discussion. In each case, these were gifts from the gods. Water, the gift of life. It is a gift provided by the elemental beings. That is captured in our Olelo no Eao, our proverbs and sayings. This one happens to be used by the Board of Water Supply. In English, it means that water is life, and Kane, who I just showed you, is the keeper of water. Well, Kane is also the name for the Kanaka, the human, the man. So, interesting enough, when they say, hey, huewai ola ke Kanaka no Kane, it says, man is Kane's living water gourd. We are created, and as we know, much of our makeup is water. And so in their Olelo no Eao, in their science native language or native science, we captured it in these terms. So as you look to many of these proverbs, we'll find these references and how they are applied to this. In this one, Ola ikawai oka opua. There is life in the water from the clouds. This again acknowledges where the water is. There are chants about where the water comes from. I am Kani, where is the water? The water is here on this land. It is in here, this pond. It is in this plant. It is in this, this stone. In this case, it is in the clouds. And when we see these clouds over each of the islands, we know that we live tomorrow because the waters of Kani are now flowing through the land. And of course, this is on that island, Oahu, on our windward side of the island. So it's critical. Oftentimes people come to the islands during their vacations and it might be raining. And they said, when does the sun come up? And I said, well, if it weren't for the rain, the islands wouldn't be green and it wouldn't be as attractive as a visitor. So we're thankful that the rain is there on a regular basis. This says, when the sky weeps, when it cries, it's not a sad thing. If anything, it allows us then to see the green forest, to plant our taros, as well as to catch our fish, because the fish are being fed by the sediments that come from the mountains as well. So to understand the relationship of the space above us as well as the lands we live on. In some cases, we actually give the names of, we name certain rains for their characteristics. The value of that is to say, in this particular place, Ka'ua Kuahine o Manoa, the Kuahine rains or the Kuahine winds is a particular kind of wind that is only found in Manoa. And so if you want to tell someone something about where water might be found, you might refer to something like this without having to tell them specific directions because they have a reference point to follow. This concept, is really speaking about the idea of let's plant trees, because trees are known to attract rain. Well, it's a metaphor to suggest that if you're going to construct and build and do things, create and think about what attracts resources. What are the businesses? What are the practices? What are the technologies? What are things that begin to have this symbiotic relationship rather than an extractive one? And so we can go back to and look to our elders and our kupuna's knowledge and begin to pull that forward. So rather than building a home that does not have a catchment system in it, perhaps we start looking at it from that standpoint, looking to our technologies that actually pull water from the air rather than just relying on groundwater. These principles and concepts were part of the fabric of the culture, clearly something that is applicable today as it wasn't to them back then. In this image, I just wanted to share that there's so many different activities. Our life was around the water, whether it was recreational purposes in canoeing or whether it was actually as a source of food in terms of ocean proteins, but just an idea of recreation and being a part of it. So this term, moale kawai kamaka okapua, really says that the flowers, the children, the produce, the products, that's what the term pua means. It's all related and tied back to water. So therefore, care for that water, care for that source, if you live fully in this way. Now, when we look at it from an engineering standpoint, bringing it into systems, I subscribe to this notion. It's an old planning model we used to use called SEPTI, which really begins to look at the impacts of the social, economic, political, philosophical, technical, and ethical impact, as well as the ecological and environmental. When we look at it from that lens, we can look at how our ancestors and those in the islands actually applied them to socioeconomic needs. In this case, this is a fish pond that is aquacultural practice right outside the Hulihe'i Palace on the Big Island. So rather than having to go out and fish and catch and shop, they've created these fish ponds right near the king's home, the Ali'i or Mo'i, so that they could go out and choose it. So this became our first refrigerators. And of course, some of you know that Hawaii and the Pacific, Hawaii is one of the early adopters and creators of aquacultural systems using fish ponds along the coastlines. So from a socioeconomic standpoint, they brought their food to them rather than having to go look for their food. From the eating and cooking and drinking, water and steam again. We did not have microwaves, but we did have steam. And underground imu. Some of you may have gone to some of our luau's or our authentic luau's, where they may actually demonstrate the cooking of our foods underground in these imu, underground ovens. These ovens just don't operate on heat alone. It does require moisture and steam. And so the water is very much a part of not just for drinking, but also for cooking and steaming. In politics, prosperity, and power, you'll find the terminology of vai, as I mentioned earlier. The term vai means anything of wealth and value. The very term for the laws of the land is known as kanawai. Ikanino ka'alai ikawai. It speaks about this kind of bird, as in this picture here, the mud hen. And it kind of relates to a person who has some prosperity. And when you have prosperity, you can speak with authority. And so these relate back to the fact that the kapu system, the rules of engagement, were driven in many ways because of water, how it was treated, where it was, who was responsible for it. So a very critical component of daily life in Hawaii. We all know if you don't have water, you can't live. Science and technology. In order to move water, they developed awai systems or ditches that would take water from major streams, but not like irrigation systems on the continent where the water runs out, maybe percolates or dries up. But in this case, they pull the water into taro systems where the water would feed the taro, work as a bioremediation methodology, go back into the stream and then down to feed other components in the system. The image on the left demonstrates a whole, what we call makaha or makaha, where they're actually using this as a gate system to move fish in and out of the fisheries out in the ocean and then to a safe place into the fish pond called the loko. So the water was a big part of our, like I said, our life, but also it created some ingenious methods of managing the water. Our agricultural systems, as you see here with the taro fields and the fish ponds, this is just an indication of the relationship of land and sea and how they related. So the waters that would run through the taro would basically slow the water down in case if it was a flood. It would capture the sediment so that it wouldn't go into the ocean and or to nearby ponds. But at the same time, it would allow water through to pick up nutrients, find its way down to a pond like the one you see in the below, the loko'i'a, and therefore then provide the nutrition for the fishermen. So we have farmers and fishermen who were utilizing the systems, a direct relationship, upstream, downstream, which we call the ahupua management system. From an astronomy standpoint, Hawaii's in the big news. We have a lot of conversations about what's going on our Mauna Kea and other mountains like Haleakala, of looking into the sky. Well, that's not a practice that is foreign to our elders. In fact, some of our astronomers, our kilolani, those that would see and look to the skies, relied on water, relied on ponds. And it's not uncommon that when you go to a place like a heiau or a place of worship or study, you would find a pond, a dark bottom pond, that would allow the seer the scientists, to make observations about where the moon and the sun, but particularly at night where the moon and the stars were located, immediately above them. So this mirror effect actually became the first astronomy or observatories for our elders, and so that they could track the time, the seasons of when to do things and when not to do things. In our culture, the day actually starts when the moon rises, not when the sun rises. And we follow the moon calendar, and it was important to be able to see accurately where the moon was rising and where it was setting to determine when we were to behave properly. So there's a saying that says, when things look down, look up. And if you want to know what's going on up above you, look down. That's the reciprocal relationship of sky and land. From an environmental and phytoremediation standpoint, I've already commented on it, but the picture in the middle at the top of the page is an old image of Waikiki, right where you are today at the convention center, which is off to the left of that image. It was all wetland. At that time, we called it Ahupua'a Momona, a place that was rich and full and abundant. It was later classified as a swamp, and that enabled policies and practices to be put in place to cover that swamp and replace it with a new source of revenue and a new source of nutrition called Waikiki. It also demonstrates that on the side, the Hawaii system I talked about earlier that goes into the ditches, as well as out of mountains and down rivers and streams. So the relationship of people and place, upstream, downstream, again, being demonstrated in these practices. Regardless of what the Olelo no Ea or proverb is, it's always a message. In this case, this is talking about how the waters from upstream are actually bringing the debris from there to the ocean. And it was important because it talks about behavior. If you want to see someone's behavior, watch what washes out of their mouths, watch what washes out of their behavior and their action. They may talk clean water, but they produce dirty water. That's a hidden concept behind this. When the source of the water is dirty, muddy water will be seen in the lowland. So if a mind is dirty, if one's thoughts are muddy, then you can probably expect their behaviors and their words to be the same. So this is a relationship and guided by our relationship to water. And the same things here, to be able to see the behavior of the practice, by seeing stones that belong upstream in your yard, you know that something occurred. And basically it's preparing for shocks in the system. Instead of a cloudburst that washes the stones from the stream beds, or of a person who, like torrents, leaves no scandal untold. So basically whatever you throw out, whatever you bring into society. So these again can go back to our relationship and clear understanding of water. And as we bring that forward, and not going back, but bring that forward, how does that begin to influence the way we design policy? How does it design our way we respond to issues of malfeasance or misappropriated planning, that kind of thing? I bring that to this point because if we look at our headlines today, and these from the headlines just of the last several weeks and even months, is that we're recognizing that at some point in time, perhaps we've ignored some of these signs. Return the water in an ongoing battle. On Maui, there's an ongoing dispute, or there has been, about water being redirected by agricultural companies that actually took water away from farmers and from fisheries and communities. And it took many, many years of ongoing discussion and legal battles to get some of that water returned. As you can see there, even the judge there was going to vacate the case because at some point in time, their practices were just not appropriate or pono. Most recently, most of you have probably heard about the impact of the fuel tanks at Red Hill and the construction process that was used many years ago. But while we may be able to forgive ignorance of the past, it's hard to forgive ignoring of the present. And so many people are concerned that how do we stop or how do we begin to adopt practices of what we call na-na, observance? How do we observe? Why would somebody build a tank that has fuel in it 100 feet over a water system? Well, if that was then, this is now, and we have seen some problems with it. Why aren't we taking quicker action to respond to those things. Again, the values, the practices, and the principles, they're all reflected. They're not new in our culture. The cries that people are having now for proper action and behavior, whether it's the Navy, whether it's the Board of Water Supply, the state of Hawaii, or any landowner, these aren't modern things. These are things that were very much a part of our cultural practice. And I would say not just here in Hawaii, but anywhere where people's water resources were at risk, whether by natural or man-made practices. At any rate, that's about what my time is today. I just wanted to share that with you, and I'll be glad to take any questions. I hope that ties into some of the other things that people were sharing with you later. But these are some of the values and the concepts of water from the indigenous mind here in Hawaii.
Thank you, Ramzi, for the wonderful, broad recognition of how water is so central to Hawaii, from the sky to the mind to the day-to-day life, and not only to the word of your state, Hawaii, the center of it is Vai, water.
Yes.
So with that, we'll move to—
Thank you very much.
Mahalo. To our second speaker, who's going to talk about water scarcity and security, followed by water, how and its relation to environmental and social justice. And our last speaker will talk about the importance of water as part of education and the future knowledge of literacy to everyone.
Thank you, Dina. I'm Kate Brauman. It is a great pleasure to be here today. I'm really pleased to talk to you about water scarcity and water security. And it's really a great pleasure to follow Ramzi. So I hope that some of the themes that he brought up are something that you'll see in this talk as I move forward. And I am going to talk about global water security, but I want to start out a little bit more local. So not totally local. We're going to leave Oahu and we're going to head to the Big Island, but we're staying on the windward side and the leeward side, and we're headed to Kona. And this rainfall graph of Kona, I think, sums up why it's an amazing place to visit. And it's also part of the reason why Honolulu and this part of Oahu are also amazing places to visit, because it really doesn't rain very much out here on the coast. Instead, we see the rain up the mountain because of these convective rainfall situations here on the islands, and the water source is up in the mountains. And so what that means is that we have a lot of demand for water down on the coast. In Kona in particular, like in Honolulu, a lot of that is new development. There's a lot going on. While up in the mountains, where there's native forest, there's pasture land, there's a lot of big ranches and upland areas throughout the Hawaiian Islands. That's really where the water source is. And those upland areas are connected to the coast. The Ahupua'a, as Ramzi said, is the Hawaiian watershed. Interestingly, in Kona, because the substrate is so young, Kona is a very young island, a lot of this substrate's only about 1,000 years old, there are actually no surface streams on the entire Kona side of Hawaii Island. So we're really looking at an entirely groundwater driven system. And so people get their water from groundwater. And we can use the framework of hydrologic ecosystem services to think about, well, if people down on the coast are worried about having sufficient water, how could we think about managing land up in the mountains and connecting that to water and then connecting that back down to people? And so we can start out by actually trying to understand what is it that happens up in the mountains and how does that affect water? And I really like this framework because it lets us think about feeding back, that land management's not happening in a vacuum, it's happening as part of this whole context of people and water together. So I would be happy to talk in depth about any of this. I will geek out about fog following the forest as long as you want, but I'm going to skip it for now and just say that we did a lot of micrometeorology up in the mountains and actually brought that to the point where we could look at how do different plausible land use transitions in the mountains of Kona likely affect groundwater recharge. This was very exciting. But it's not far enough, right? Because people don't drink recharge, they drink water that's in an aquifer. So we worked with the USGS to actually continue the modeling this cycle, this pathway of water from recharge all the way down to where people are pumping groundwater. And what we found is that there are actually measurable impacts of these changes to the water table. And we even took that one step further and looked at what the cost savings from having more water would be, or the actual cost of having less water would be to the water department. Super exciting. People talk about ecosystem services all the time, but actually going all the way through we were really glad to be able to do that. But one thing that you might notice looking at this is that these numbers are not actually very big. We're talking about 2 to 4 feet of water loss in some transitions, maybe up to 10 feet of gain in water in other transitions. Why is this so small? Well, it turns out that in Hawaii, another really interesting thing that's happening is submarine groundwater discharge. And functionally, what this is doing is dampening the signal of what's happening up in the mountains in terms of how high or low the changes we see in groundwater are. You might think about this as wasted water, since it's fresh water that's moving directly out into the ocean. But that wouldn't be totally correct, because that submarine groundwater discharge is actually really important for supporting really critical habitats on the Hawaiian Islands. These anguilline pools are brackish pools that are filled with both fresh and salt water. They support really interesting biodiversity and fish. The original fish ponds that Ramsey was talking about were frequently built using these, and they're a really cool piece of the environment here. If you get a chance to go to the Big Island, these are both pictures from Kaloko Honokohau National Park. And so, I set this up by saying, oh, ecosystem services is a great way to talk about water and think about, how land cover affects water, affects people. But really, we have to, even when we're just talking about water, we have to explode this diagram to think about the whole range of things that changes in land cover affect. So climate, because we're sequestering carbon on the landscape. There are amazing endemic bird species here that are supported on these landscapes, lifestyles like ranching, even the goods that are harvested from the land. And it's not even just water as a single thing, right? We have to think about both drinking water, but also, for example, supporting these anguilline pools. And so when we think about sort of the context of water availability and water scarcity, it all ties up into all of the different things that water is being used for. And so there are 3 themes, I think, that come out of this that I'll talk about globally, but that are really illustrated by what's happening here in Hawaii. So when we talk about water scarcity and we talk about water security, definitions really matter. How we define this and what we're thinking about, what our narrative is very important. We have to think about what we mean when we say wasted. Values are important. Who is using this water? What are they using it for? And is it really wasted? And certainly context matters. Thinking about the distribution and equity of the distribution of water is at least as important as the volume of water that's available. So I want to start by using a couple of pictures that you may have seen in the past. We often talk about how little fresh water there is in the world. These images are from the USGS. Fresh water is only 3.5% of all the water in the world, and water in lakes and streams is just a tiny percentage of that. And we're telling this narrative about how scarce water is. But if you ever take a look at these, the major source for all of the figures that go into this is this guy named Igor Shiklemanov, who worked at the Russian State Hydrologic Institute. And Igor wasn't actually interested in water scarcity. He was interested in water abundance, because it turns out that the Russian Arctic has a huge amount of water in it, and the Russian government really wanted to know how much was there. And so they sent Igor out to try to figure out, in these ungauged giant catchments, how much water was flowing out of these rivers. And his approach worked well enough that he actually then took this and used it to quantify world water resources, worked closely with the United Nations, and it's his work that still gets cited regularly. And his numbers were pretty good. They're well within the bounds of the things that we're seeing coming out of global models today. And so I might suggest that we switch this script. We at least could flip this script and talk about how much water there is in the world. What you're looking at here is a map based on data from the Water Gap 3 model, which is run in Germany. There's about 15,000 watersheds in this picture. And the units here are cubic kilometers, which is a lot of water. So I think if we want to understand water scarcity, we need a definition that considers what we want to use water for and whether there's enough for that. So do we use a lot of water? It turns out that's a really hard question to answer, and we don't have good numbers about it. At a global scale, the Sustainable Development Goal 6 is starting to try to put some numbers on this, but it's all modeled. So when people model water use, they think about 5 big things. They think about irrigation, they think about livestock, they think about domestic water use, industrial water use, and thermoelectric power, so cooling for power production. And really quite consistent globally, it's irrigation that's the big water user. And there's a couple reasons for that. One of them is that it turns out that if you spread a lot of water over a large area, that's a really great way to cause it to evaporate. But it also turns out that for most of these other uses, when you think about using water in your home, even if you take a really long shower, you're still sending that water down the drain and back out to be used potentially again. That's much less true with irrigation, although it is also true with irrigation. And so the bottom line is that big water users irrigate. It's not actually possible to use all that much water unless you're talking about irrigation. So what I'm going to show you here is just a simple bar graph. There are actually about 15,000 lines on this, and it's for each one of those watersheds how much water is being used by sector. And what you can see is that this looks like it's a graph of irrigation water use. If we zoom in, it turns out that it's not. There's lots of little pieces of these other water uses on there. It is a stacked bar graph, but you can't tell that. So I'm gonna, instead of just showing you this total water use right below, lined up vertically for each watershed, what I'm gonna show you is fractional water use. And that's what you're looking at here. So if you're using a lot of water, it's going to be almost entirely irrigation water. If you're not using a lot of water, it's actually a whole mix of things. Livestock definitely has a big role to play here, but you can see those little lines throughout this graph showing you electric, manufacturing, domestic. Depending on what watershed you're in, lots of different things could be driving your total water use. But again, we have to come back to this question of context. Are we using up our water? Is using a lot of water a big deal? Is that a problem? And I really like to think about that by looking at water availability. So again, this same graph, and then water consumption. And what's important here is 2 things. First of all, these 2 patterns, they're not the same. We are not using water in the same places where water is available. And that's really important. But there's something else that's important here. So I talked about how the water availability is in units of cubic kilometers. This water consumption graph is actually in units of cubic meters. When I change this into cubic kilometers, the picture looks pretty different. And when we just look at an annual basis, what the ratio of water availability to water consumption is, it actually doesn't look that bad. There's a few places where we're really using basically all of the water that's available. The High Plains Aquifer in the central US, parts of North India, Central Asia. But I mean, I don't know, I look at this, I think it doesn't look that bad. I also think it probably doesn't jive with what you understand about water and water scarcity. And that's really because that's on an annual basis. And we don't use water annually. We don't turn the tap on once. We want to be able to turn the tap on all year long. And so we have to think about dry periods, dry seasons, and also dry years. And that's what you're looking at in this graph. So those dark red places that are chronically water scarce are still on there, but now that's fleshed out. So there's bright red color on there. And what you're seeing with that is seasonal water scarcity. That means every single year, there are periods of the year where the amount of water available and the amount of water that's demanded are coming into conflict. So that is definitely water scarcity, but it requires really different management solutions than if you're chronically water scarce. Similarly, the places that are showing up in orange on this map are water scarce in dry years. So not even on an average year are there periods of time, months, that are water scarce, but on a semi-regular basis, there just isn't enough rain. what we start seeing again is, oh my gosh, we're starting to hit that limit of how much water is being consumed compared to how much water is available. And what did I say? How do you use a lot of water? You use a lot of water for irrigation. So do we blame the farmers? Yes, big water users irrigate, but let's dive into this again and look at this, except this time, instead of having fractional water use underneath, I'm just going to show you what the water depletion category is. So again, that dark red for chronic all the time, moving to the cooler end of the color scale for using less water. And I love this graph on the bottom because it's ugly. There are patterns in it. It's bluer on the left, it's redder on the right, but there's a whole mix of things happening in here. What I'm going to do to make this a little clearer is actually rearrange these two graphs. So they'll stay vertically aligned. The amount of water use is going to stay aligned vertically over the water depletion category below. But instead of making this least to most absolute water use, so that top graph makes sense, I'm going to do least to most depleted, so the bottom graph makes sense. And what you can see when we do this is that if you're really water depleted, it's likely that there's a lot of irrigation use happening in your watershed, but there's likely lots of other things happening too. And there may be no irrigation water use at all. At the same time, there are actually plenty of places where less than 5% of the available water is being consumed, where there's a huge amount of irrigation going on. And so context really matters. There's never going to be a one-size-fits-all solution to this. And yet we know that when we talk about water security, we have to think about that context also. So this is, again, this map that's really showing this biophysical measure of water shortage, how much water is being consumed. And this is a map of water conflict. This is from Oregon State, which has this really great transboundary freshwater dispute database. And the critical thing here is that these maps don't align at all. In fact, Oregon State has done really nice research showing that it's much more likely to see cooperation than conflict when in places that are water short. And yet we know that there are pathways to water conflict. And what's becoming increasingly clear is that water stress, yes, is about the absolute volume of water that's available, but it's also very much about access, about allocation, about equity, and about risk. And we have to think about all those pieces when we think about the pathways from water scarcity to water security to instability. This is an image from the Department of Defense Climate Risk Analysis, which came out just this last summer. And what's highlighted here is that direct water issues all the way through their primary and secondary impacts have security implications that range from altered planning environments to increased likelihood of migration. And we need to start integrating all these pieces and understanding them if we want to understand water security. So I'm going to summarize, and then I'm going to give you a plug. We have to think about language and the stories that we tell. Are we telling stories about water shortage or water abundance? Are we telling stories about how the end is near or about how we can make change and make things better? And we need to recognize how we're using water and how we value the ways that we're using water, even water that we might think of as wasted. And we have to think about the distribution and the equity of that water. Are some people having more access, being able to use water in different ways than other people? And is that part of what's causing the conflict, or is it actually an absolute scarcity issue? So I will end by saying that I am now at the Global Water Security Center, and it's quite clear in my world right now that decision makers care about water. They want to know about the kind of science that's happening here. They want to know about water. And they also don't have any idea what to do with the science that's available. They don't know how to parse it, but they also quite literally can't get access to it most of the time. And so researchers who are doing science that is potentially really relevant aren't actually having the impact that I think a lot of us got into this business because we want to have. And so I will just say, find the boundary organizations. It's a big stretch to get into operation, into action with science and science data. Some of you may want to do that, and that's awesome. I highly recommend that. But not everyone will, and that's why boundary organizations exist. Take advantage of them and work with them, because there is this huge need out there, and we can do so much cool stuff. And I will end there. Thank you so very much.
Hopefully, can you guys hear me okay? I'm very tall. Is that good? Okay. Yeah, so thank you, Kate, for that great presentation. And yes, it did set me up quite well. So my name is Abigail Tomasek. I'm a new assistant professor at the Department of Crop and Soil Science at Oregon State University. I'm also in agricultural extension, so while I have a research component, 70% of my position is also going out and talking to farmers and trying to bridge the relationship between farmers and regulators, especially with water. So with that, my talk is called Advances in Social Justice and Resiliency and Water Resources. And so I'll start out again by saying I'm not a social scientist. I was trained as a civil engineer. And thank you, Adina, for giving me the opportunity to talk today. I'm also a new career, early career scientist. And so it's a great honor to be here with these experts. And I think this is also something that is important, is to involve early career scientists in this discussion. I learned the hard way more from things not to do than what to do. So having conversations with experts in what to do from the beginning makes the situation much easier. So with that, I feel as an early career scientist that I need to give credit to the people that this was based on an AGU session in 2021 with my collaborators, Sarah McMillan at Purdue University, who is my postdoctoral advisor, Fuchsia Ann Hoover, who is now a new assistant professor in UNC Charlotte, and Rachel Scarlett, who is doing really great work with the Field Museum in Chicago. They both do work with stormwater and social justice in that aspect. And so this just gives a quick list of who was involved in that session, all who are early career. And I can't cover everything with social justice and resiliency in this talk, but hopefully this will give you a flash idea of everything you should consider and make you consider too in your research how you can incorporate this. And so first, how you define water equity. And I think if you guys were here during the presentations yesterday, Nicole Crane had a great thing that's saying that you have to be careful with definitions because definitions can be dangerous. How do you define water equity? Equitable for who? Equitable when, right? And knowing that that can be transient and very independent for who's talking about. However, most of us come from a geoscience background where you have hypothesis and you have conclusions. So having some kind of definition to start with really is helpful, but remembering that this is a flexible definition, right? It can change with time. And so this picture obviously shows, I'm sure most of us, well, this is also an international crowd, but talking about Flint with an issue with really poor water quality that was largely in a minority city. And so with that, by definition, people should have access to clean water. It's in the United Nations goals, right? But when you look at this, so this was based on a literature review looking at the availability of water across different categories, things like age, things like racial makeup, and looking at, if you look at this, you can see that your water hardship is not the same across the board. It's associated with rurality, indigeneity, education, and age. And so this is a quick summary, that this represents a national environmental injustice. And so just a quick run through, this looks at water quality across the country. And so with the darker colors, that dark blue represents not only water violations, but also the populations of color. And you can see that this is very segregated. For those of you not from the US, Arizona and New Mexico is very dark blue, and this has a large percentage of tribal members. And also they've seen that these are, problems with water quality. And in these communities, not only is there a bigger problem with water quality, but these violations go on longer than in non-minority communities. And then this picture shows sanitation. And so again, you can see the same situation where these regionally segregated areas of sanitation. And so one estimate says that about 48% of households on reservations don't have adequate sanitation. They've also shown that 20 to 30% of people on reservations are not connected to a septic system compared to 0.5% in white majority neighborhoods. This again is a huge racial injustice. And with these changing climates, with reduced rainfall and droughts, as New Mexico and Arizona are experiencing, this problems could be exacerbated in the future. And so again, for the people that are familiar with the US, historically you had something called redlining, where neighborhoods were ranked AB or CD. And these CD neighborhoods were redlined. Basically, you were not able to get mortgages in these areas. So it created this racially unjust makeup in cities. And so this graph at left shows the percentage of homes that are facing flood risks for green lines, so these good neighborhoods, and these red line, these bad neighborhoods, along with a picture of Sacramento, which was the most racially unjust. The blue shows the areas of flooding, and the red shows these red line neighborhoods, and you can see that there is a big overlap between these red line neighborhoods and the areas of flooding. There's a long history of this. Usually people with marginalized communities were put into areas that flooded. Also, there's less resources for improving these neighborhoods when flooding does occur. And also remembering that you are also talking about communities that are struggling to survive as it is. They have less ability to adapt to these flooding problems in the future. And again, with climate change, this problem might be exacerbated, will be exacerbated. And so with that, thank you, Kate, also for aligning, because both my case studies are in areas with big water problems. So I am new to Oregon, but Oregon, like a lot of the West, is experiencing an incredible drought. I'm not from the West, and I was dropped down in 2021 with a big water crisis. And for those of you that also aren't familiar with the West, you have things that are water rights, which are completely, I don't want to say ridiculous because that will get a little bit political, but basically it started from the gold rush in California. There's the first in right, first in time. You arrived on a land first, you had the water right. And so this picture shows the Klamath Basin. When I started in Oregon, I was told if you can spend your entire career working on the Klamath Basin, and if you can solve any problem, you're doing good. So I'm going to try and give you a rundown in about 5 minutes on this. So the picture of the left shows this basin, and you can see that there is a huge, so the area in orange is the record driest in this basin. And the picture on the right shows there's a large number of tribal communities in this basin. And what's interesting is you have tribes in the upstream and you have tribes in the downstream. And this watershed is very complex. So the picture at the left, it's a little bit difficult to see, but you have a lake above, that's Upper Klamath Lake. Then it goes into something that's called the Klamath Project, which feeds into a lot of irrigation and a lot of, it's 150,000 families, no, that 200,000 acres. I don't have my notes, but a lot of families. And so when you think about that, and then the water also is diverted through the Klamath River, and then the Yurok tribe is at the bottom of this. And so when you think about this, as Kate said, irrigation uses a lot of water. You have people that are farming alfalfa in the desert. It doesn't always make sense. But I'm part of agricultural extension. My job is to go out and talk to farmers, and talking to people. You have people that have lived there for 100 years, and you talk to them and they say, my grandfather farmed, my kids want to farm. I morally can't tell them to farm. What are we supposed to do? In these areas, in Oregon, these farming communities are in really poor areas. The question is, where do I go, right? And so when you're talking about water justice, you have tribes, but you have farms, you have a lot of complexity. And when you don't have enough water, how do you allocate that water? And so with this, because there was such a drought, so for both these tribes, for the Klamath tribe and the Yurok tribe, fish are a very important aspect of their culture. In the upstream, in Upper Klamath Lake, you have suckerfish, which is an interesting also dynamic, because if I asked you want to eat a suckerfish or a salmon, I would assume the majority of you guys would say salmon, right? Suckers have a notorious bad image. They are called trash fish, which is also a political term. And they showed, there's a literature review that showed these sport fish, things like salmon, have 11 times the research or research journals as opposed to these rough fish. And so when you're talking about words and meanings, and you're talking about water equity, talking about trash fish and the preservation of something that's sacred to people, it causes this divide when farmers start to say, why should I preserve this trash fish? And then so basically the tribe, the Klamath tribe was able to get water rights above the farmers, which was a great thing. But now they can hold water up in Upper Klamath Lake which then decreases the water down to the Yurok tribe and has issues with the salmon population. So communities that should work together, the tribes have shared interests, are at conflict. Who gets the water again? And so with this also complicating the problem, there's at the bottom of this watershed through the project, please raise your hand if I'm getting too late. It also, I'm a talker. It goes into a large wildlife refuge, which is really important for the Pacific Flyway. And with this, when you don't have water, then the birds don't have anywhere to go, and you also end up with problems with botulism. There was 60,000 birds that were killed this past year because of an outbreak of botulism. The picture at the bottom shows the irrigation water allocations for these farmers. You can see that's decreasing over time. And the picture at the right shows the abundance of the fish, and you can also see that that is declining over time. And so again, when you have not enough water, how do you decide who gets the water and who decides that? Which tribe gets the water? Which fish gets the water? Farmers, do they give up their water? Does the wildlife refuge get the water? It's a very complicated situation when there's just not enough water to go around. And there was a really interesting work between these four completely disjointed stakeholders, if you will, to form what they called the Klamath Agreement. These people came together, the three of the four tribes signed on, the farmers signed on, and they came up with an agreement. And then, after years of work, Congress didn't pass the bill in 2014, I think it was. And so now talking to farmers, they say, why should I care? Why should I get back into this when all of our work wasn't appreciated? And so it's a very high conflict area right now that has very difficult solutions. And this quote I thought it's all encompassing of the water problems now. We need creative ideas, we need inspiration, we need community building. And so similar, this is another case study from my postdoctoral work. Even though it's 8,500 kilometers away, the issues are very similar. So this was part of something called the Arequipa Nexus Institute. It was a partnership between Purdue University, where I got my postdoc, and a university in Arequipa, Peru. The project had two objectives: to solve problems of regional importance and also to capacity build at this public university, because research was a newer thing there, so trying to do two objectives. And so this is just like to give credit to my collaborators at Purdue and at Universidad Nacional de San Agustin in Arequipa. And so just to orient you, Arequipa is located in the south of Peru. I think, Kate, this was also listed as one of your areas of water conflict. It's a very arid region, but with this arid region, you have a river that runs through. This river provides water for all of the stakeholders. And this area has been farmed for thousands of years just because it is a fertile valley. So this picture at the right shows these historic farms in the floodplain of this area. And so this is the importance of a reminder of the importance of stakeholder involvement, and how I said it was a rough learning curve from the beginning. We wrote a proposal. There's what's called the Cerro Verde mine in the outskirts, about 25 kilometers outside of the city. It's one of the largest copper mines in the world. And we went in thinking, okay, there's a copper mine here. The farmers are worried about bioaccumulation. And to collect the soil samples, we had to start talking to the farmers, and we realized that the problems were much more complicated than simply bioaccumulation. You had ecological stressors and you had social stressors, and in some cases they were more worried about that than the actual metal bioaccumulation. And this is the picture showing all of how water is organized in the city. And it's a little bit overwhelming, and it also brings to light how complicated it can be. And if you think about this, if you're a farmer, you're way down on the list of these stakeholders. So if you have an issue with your water, trying to figure out who to talk to can be very complicated. And this picture is from work that I did with Zach Bruckeisen, with looking at a lot of these areas don't have large historical data, so we use spatial imagery to try and extract out the land use change. So the picture at the left shows in 1966, and the picture at the right shows 2022. And with this, you can see big changes. So in the middle of the area, from 1966 to 2022, you had large agricultural expansion. Like a lot of countries, there is a lot of rural to urban migration as people go to look for better opportunities, largely from the impoverished mountainous area in Peru. And Arequipa is Peru's second biggest city, so this is a big deal. And so you can see the formation of informal settlements along the periphery of the city. You can also see urbanization, so the expansion of the city core into these historic agricultural areas. And this picture shows breaking it down to irrigation districts along with the land use change on the right. So this shows just percent of agricultural land over time. And one area I'd like to point out is a really traditional farming area called Kaima. And this shows the difference in the situation. It's a microcosm of kind of what's going on in the city, where down near the urban core, you have very high quality living. It's some of the richest people in the city. Then you move to the middle of the district and you have people that are traditional farmers getting by. And then you go to further up and you have people that are living in complete poverty without any kind of services in these informal communities. And this picture shows as a schematic I'll show throughout this if I don't run out of time, but looking at the stakeholders that you have in the city. So you have this one river, you have hydroelectric, you have industries, you have a mine. Okay. Yeah, and you have residents, and you also have, like I said, so the Cerro Verde mine. And you also have the formation of these informal settlements. In this picture, they are separated because currently there are no services to these informal settlements. And this sets up kind of a dynamic of farmers versus migrants. And with this, because the migrants don't have, these informal communities don't have water, then you need to get water somehow, but you're already talking about an over-allocated river. Everybody should have the right to water. I think we can all agree about that, but what happens when there's not enough water? How do you get water to people when there isn't enough water? And the farmers begin to blame both the state and the migrants, and the farmers are largely indigenous, and the migrants are largely indigenous. So again, setting up people that should work together to promote their rights in conflict with each other. And this picture shows right now what's happening is people are going to because there are no services, people go and illegally extract the water in tankers and move it up to these informal communities and sell it. But you can see these canals are open to the environment. There's big problems with pollution, and they also sell the water for a big expense. So then you have injustice there because you're already barely scraping by and then paying for your water that's not potable to begin with. And also looking at this, so the arrow shows that what happens when you divert water to these informal settlements, then you have farmers downstream. So the picture at the right just shows the diversions in these irrigation canals. The red areas show people further downstream. And so people pay for this water. What happens if you illegally extract the water? Then there's less water for the farmers downstream that have paid for this water. And so also setting up the mine. So the mine wanted to expand in recent years. There's not enough water, like I said, so what they decided to do was to build a wastewater treatment plant, which sounds great. There is untreated wastewater entering the Chili River. So they're going to build this wastewater treatment plant, treat the domestic water, and then use some of the water and release the treated water to the Chili River. It sounds like a great idea. But then we were out there during our field visit and noticed that the effluent entering the Chili River did not look so clean. You can see in the picture at the right, the dark brown is the effluent and the blue is the Chili River. And we collected nutrient concentrations downstream of this river, and the concentrations of ammonium and phosphate were huge, and so was the DOC. This is indicative that this is probably not treated wastewater. Again, this is not saying the mine is bad, it's saying that you have to be cognizant of how these relationships work, and using this maybe as a way to get water and to build people's trust. The mine is now viewed in a public light because they're investing in these water services. But is it to win the access to water, or is it actually to do good? Okay, I will quickly go through. So yeah, just since we talked about this a little bit in the beginning, so similar to what they were talking about with Hawaii, these indigenous terracing is one option to build resilience for when you're talking about climate change. This is a quote talking about how with terraces, after 6 months after they irrigated, they excavated and the water was still damp. These have been used for thousands of years in Peru. And also there's projects currently in Lima. Lima is the second driest capital in the world, looking at trying to revitalize these indigenous canals as a way to store water during their wet season, to have more water available during the dry season. And so showing that there's these indigenous practices that might not be founded, you can learn from traditional ecological knowledge and apply this as water conservation strategies these days. So with that, I think I've talked for a long time, but just a reminder to some potential action items that you can use, and just really a consideration to step back, look at it from an ecosystem perspective, look at all the stakeholders, really go into the community, find people you trust and learn from them, as opposed to going in with preconceived ideas. So that is my talk. Yes.
Thanks, Abigail and Kate and Ramsey. My name's Tom Meixner. I'm a hydrology professor at the University of Arizona and also the department head for hydrology and atmospheric sciences, if the shirt did not give it away. I'm going to talk today about hydrologic education, and particularly some work I've done in a field course, and then some work I've done with something called Project EDDI, and then some citizen science work I've done on GI rapid assessment. I particularly want to recognize my colleague Ty Foray, who's taught field hydrology with me for almost 17 years now, who I learned a lot from. And then on Project EDDI, Catherine O'Reilly and Rebecca Gochis of Illinois State, and Dax Soul of CUNY Queens. And then for the GI rapid assessment, Jennifer Cherrier and Allison Downey at CUNY Brooklyn, as well as Alan Berkowitz at the Carey Institute. And with that, I'll get started by going, by reminding you that the University of Arizona we respectfully acknowledge is on the land and territories of indigenous peoples. Today, Arizona is home to 22 federally recognized tribes, with Tucson being home to the O'odham and the Yaqui. Committed to diversity and inclusion, the university strives to build sustainable relationships with sovereign native nations and indigenous communities through education offerings, partnerships, and community service. And we'll come back to the O'odham heritage because it gives Tucson its name. So I'm a hydrologist, but also a biogeochemist. And what I've learned over my career of educating is that engaging people with water builds their understanding of place. I study arid and semi-arid rivers, I teach a variety of courses, but ultimately what I've learned from students over the years and colleagues is that water is personal and about place. And water, and thus hydrology, permeates the environment and our existence. And importantly, learning about water connects people to their place, and I hope you'll see that as a theme running through my presentation. Right, so hydrology, simply the study of water's movement in, on, and through the earth, right? There are fundamental principles and processes, and those exist. We have representations of them, but people understand and interface with hydrology through a fundamental sense of place. Water in Hawaii, or Los Angeles, or Tucson, or New York, or Moscow are similar. Same physical principles apply, but they are different, and people think about them in different ways. I think, as you've seen my predecessor presenters note. Right, this fundamental attribute of hydrology as giving people a sense of place creates educational opportunities. And I'll discuss three efforts: our field hydrology work at the University of Arizona, this Project EDDI work, and a citizen science effort with Earthwatch and HSBC. And I hope you'll see through this also that inquiry and open-ended assignments teach effectively and introduce students to the concepts of water and place in ways that are more than factual, but give them the critical thinking skills they need to address the world's problems. Okay, so field hydrology, just a little bit of background. We teach this course over the spring semester on Friday afternoons, and then we have a one-week intensive field experience at Dead Horse Ranch State Park, where the students build on a water budget. Weekly, we go over individual methods, but the students also do integrative projects and assignments on the Santa Cruz River, and then this integrated water budget project at Dead Horse Ranch State Park. So our work on the Santa Cruz focuses on something called the Heritage Reach. And this reach is, in the O'odham language, was Chukson. It does not do well in in English language, hence why we call it Tucson. But that is an O'odham word for valley at the foot of a black mountain. And that valley at the foot of a black mountain was the Santa Cruz River, which was perennial for thousands of years. It's been inhabited for over 5,000 years. And it's a special place because there was perennial flow in the desert. It was a key connection point between Mesoamerican cultures and North American indigenous cultures. That's now been created with reused effluent that's been discharged in the river by Tucson Water for a variety of reasons. But that creates a specific educational opportunity for our students over the spring term. This may come as a surprise, but hydrology students like water, hence why they've chosen their discipline. And the fact that this is close to campus, in a real place that the students can see regularly, creates real opportunities for open-ended investigation. Students can come up with a question and then investigate it, and that's what I'll talk about in just a second. Right, the Santa Cruz has changed dramatically. On the bottom left, you see the Santa Cruz River in the early 1900s. We had a river with cottonwood trees and a perennial river. And in 2010, it looked like the river on the right. We completely desiccated the river, first through surface diversions, but of course, ultimately through the great power of the submersible pump, we dewatered the aquifer. And today, it looks like this, having been rewatered. And the particular little project I'm going to talk about here that the students did this spring was one of 4 different projects that the students pursued, but this one wanted to look at nutrient concentrations in the stream and then in the sediments below it to see if there was some sort of nutrient processing going on the stream. Now, a semester sounds like a long time, but students have to spin up on methods. But on the left, on the bottom, you're seeing a figure of and then a photo of just a classic Reynolds tank, a falling head permeameter test to get at hydraulic conductivity. So a pretty simple hydrologic measurement test, but the students use that in conjunction with nutrient measurements of the sediments and of the pore waters. And what they found was indeed that there was a lot of nitrogen in the stream because this is treated effluent, no ammonia, thankfully, because our treatment systems are pretty good now in Tucson, but high total nitrogen, 4 milligrams per liter. And then in the sediments, dropping down, 600 micrograms per kilogram of total nitrogen in the shallow sediments and decreasing deeper down. So there does seem to be some attenuation of that nutrient as you go in depth in their sediment measurements. Now, they also wanted to think, okay, maybe coarse sediments or fine sediments have different treatments. And here you see a nice graph showing the concentration that they found of nitrogen and total organic carbon on the y-axis and hydraulic conductivity on the x-axis. As you can see, there is no relationship. And this is the nature of open-ended investigations, of course, is that you'll have a hypothesis that maybe higher hydraulic conductivities will have higher concentrations, and then you, of course, discover it doesn't. But the students learn about the processes, the mechanisms, their measurement techniques through this process. Okay, so on to the water budget project at Dead Horse Ranch. Right? The water budget is the most fundamental building block of hydrology. Oftentimes I will tell students, look, what is a hydrologist? A hydrologist is someone who, when they look at a problem, the first thing they think is, well, what's the water budget? Where's the water coming from? Where's it going? What are its stores? How are those things transforming water? And so we take the students to a state park, Dead Horse Ranch State Park in central Arizona, north of Phoenix on the Verde River. And what you see on the upper left is them installing a weather station with an evaporation pan to the right of the photo. And then on the bottom, you see a collective picture of the students who collected the data I'm about to talk about. Now, this is a state park. This map is to sort of illustrate that, right? A very classic American state park map. Notably, in this map, there are 3 ponds, and that's the main consumptive use of the park. In fact, one of the motivations we give to the students, and it's a real motivation for the state parks, is we're there to quantify their water right. As Abigail noted, right, first in time, first in right is a thing in the West, but one of the things you have to do to legally defend yourself is document that you've been using that water on a continuous basis since whoever you bought it from or your ancestors started using that water. So the students go about building this water budget. And so this then is a map of the park that includes their notes of the fluxes of water. And one of the key advantages of this park for an assignment is there's a specific inflow of water to the park. It's an irrigation ditch called the Hickey Ditch that's been in place since the 1850s. And then that moves through the park. There are various diversions, some back to the river, some to the ponds. There's seepage losses, there's evaporative losses. So they're able, the key here for the water budget is in real systems, oftentimes our water budget is a little bit unconstrained. We can try to measure precipitation, but anyone who's done that can tell you precipitation is spatially variable, it's difficult to get a hold of. You can try measuring fluxes out, but good luck in Kona where there's a large groundwater system and taken decades to quantify that. But the students learn here, like, you have this, you know where the water comes from, you know where it goes, and you still have difficulty closing the water budget, as you'll see. And so here's just one sort of simple water budget where one of the groups took 2 different parts of the ditch. And you can see on the right sort of the percent difference, 100% difference and 350% difference, right? So there's problems in their water budget from the simple conception they had is, well, if you measure what goes in and out and get some reasonable estimates of seepage from hydraulic connectivity, from seepage pans, we'll be able to close the water budget. Not so fast, okay? And one of the reasons for that is the gentleman on the left here, who's the park superintendent, who's holding a stop sign that is also used to divert water out of the irrigation ditch to irrigate some trees. So good luck in the Klamath, Abigail, because I'm sure the exact same thing happens there. So right, serendipity happens. People are doing this while you're there and you don't necessarily know what they're doing. We also do have them measure potential evaporation, like I said, using the evaporation pan on a long-term basis, but then a meteorological station to do continuous. And here you see those estimates. But combining all these measurements, seepage, stream flow, evaporation, the students are able to get a pretty good tight handle on the water budget of this park. Apologies for those of you from civilized nations. I am using the English units or imperial units that we use in America for water rights purposes. But right, you can see about 2.5 CFS diverted from the river. Most of that actually just flows back to the river, but there are significant losses to evaporation, to seepage. But ultimately, about, in this case, a little bit to evaporation, about a CFS, a little bit unquantifiable, but notably here, change in storage. So one of the things that students learn is that these ponds, their stage changes, and the ponds are large. They're 20, 30 hectares total in area. So small changes in stage lead to large changes in storage. And so they learn to appreciate, again, these nuances of the hydrologic cycle and water budget. Okay, so now for the other two vignettes. So I've been involved with, like I said, Catherine Riley and Rebecca Goges and Dax, among other people, with something called Project Eddy for the last couple of years. We're a group of educators across the United States working on creating engaged pedagogy for the earth, environmental, and ecological sciences through the use of real-world data, the same sort of data we use as scientists. And this community produces learning modules with those real-world data sets, and we're open and actively recruiting new members constantly. And our work focuses on really trying to help our students develop quantitative reasoning with disciplinary data, right? Things are disciplinary, there's a disciplinary context, there's mathematical methods, but there's also this critical thinking, and the nexus of those is this problem of quantitative reasoning that is critical for our students going forward. The modules focus on relevant topics, they're question-driven, they're open access and large data sets. So one example, the climate change data set uses the Mauna Loa CO2 data set, uses the Goddard GISS global temperature data set. So the students using the same data that we use as scientists. Open, large data sets, any software, Excel, R, some people are using Python, and it's a scaffolded structure. Essentially, first we walk the students through part of the assignment, then we guide them through an analysis, and then we let them explore on their own. It's flexible and adaptable. It's used as we sometimes say, K to gray. It's been used all the way from K-12 up to community science. Okay. And the participants come from large R1 institutions, state universities, community college. Sometimes it's in lectures, sometimes in lab classes, sometimes carefully led, sometimes largely students left on their own. I just want to give you an example here of, again, how this ties back to place. Chip Small at the University of St. Thomas in Minnesota developed one on quantifying nutrient processing rates in freshwater estuaries using a hydrologic mixing model. Okay, so students in Minnesota or students working in estuaries can do this and tie it back to a place that they're familiar with. Nick Bader at Whitman College developed one for string discharge that I helped him with, right? And the advantage of this is the module, you have a stream gauge on your campus, near to where the student comes from, near where there's an interesting problem for them. They can do this module for that place. And then the final module I'll talk about, Elizabeth Farrell at CUNY Queens developed one on green roofs, right? And this will help segue into the next thing on GI. But right, again, why'd she develop this? She's working in an urban campus in the city of New York, which has significant problems with stormwater. The students can relate to this. They can identify with it. They know that there's combined sewer overflows in New York because it's in the press there. and again, connect to the students and their experience. So I encourage you to dive into EDDI. We're always interested in new folks engaging with us on any sort of module. We're community teachers engaging with students, and modules can be melded to your place. You don't necessarily have to develop one. You can take one and use it as you wish. Okay, so the final vignette is about the rapid assessment program that I developed with my colleagues, like I said, at Brooklyn College and the Carey Institute, for looking at urban green infrastructure. And we did this with citizen scientists through the NGO Earthwatch, as well as the bank HSBC. I want to note sort of my colleagues, Brian Smith and Jose Pilich from earlier on in the project from Brooklyn College, and then Jennifer Cherry and Alan Berkowitz. And then in the second year of the project, Allison Downey and John Mara at Brooklyn College also joined in. Okay, so what was this? Okay, so this was a research project, essentially a one-day workshop for HSBC employees that Earthwatch and us as university scientists collaborate on in 6 North American cities: Vancouver, San Francisco, Chicago, Buffalo, Toronto, and New York City. All these cities had combined sewer systems, and so had problems with stormwater overflows and surface water contamination as a result. And we specifically focused on green infrastructure and focus on bioswales. And critically, we also had local partners, either in most places, both municipal partners from the city government or county governments, as well as from NGOs. And we did a variety of different things in this, and I just want to give you a taste, but this is an example of how sort of citizen community science can help expose people to nature right where they live, not nature as some disembodied thing that occurs in other places. So they mapped green infrastructure, they mapped the drainage areas to them, they looked at green infrastructure function through hydraulic conductivity measurements of infiltration, and also core samples that were shipped back to the University of Arizona, and also longer term soil wetness temperature data using data loggers. So just a taste of the data they collected, right? We calculated the area of bioswales in each of these cities by 2 different methods, essentially length and width, basically people assuming they're rectangles, but then also essentially sketching in boxes. And you can see the 2 methods largely cohere with each other, but there is variation, and there is uncertainty in data collected by citizen scientists or anyone. We also mapped just the vegetation. One of the challenges with GI is green infrastructure gets put in place and people design it, assume it works, and walk away. Cities don't necessarily know they're working or not until someone goes and looks. And so, for example, here Chicago learned that a lot of their plants had died, hence the very large fraction of bare soil in their systems, whereas San Francisco, Toronto, and Vancouver have fairly healthy systems. And one sort of final bit of data from this work, we did this work in 6 different cities. I'm just showing you a subset of this data, comparing those field infiltrometer measurements that the community scientists made from HSBC, as well as some laboratory measurements we made from those cores back in Tucson. And, there is disagreement among the 2. We'd expect that because of scale and methodology, but the data is largely coherent with each other, which reassured me that the relatively quick methodology that we had these citizen scientists use out in these bioswales is actually pretty effective. Okay. So to summarize that part, right, so these people participated in a science experiment, essentially, in observational work. But from surveys, from discussing things with them, these participants learned about water in their cities. Many commented that they hadn't thought about water, hydrology, flooding, any of these problems in their city. Just wasn't on their mind. But by engaging in data collection, they were able to see how water flows in their cities and maybe take action in the future. Okay. So to summarize, right, water is all around. It's everywhere. It's constant in our environments. Well, except maybe in parts of southern Peru and northern Chile, where it almost never rains. And lots of ways to engage with people and students, and I use that term broadly, learning about hydrology. In the field through exercises or investigations, in the classrooms with big data to take the place they're from or are and make it real, and in your town or on your campus with community science. And with that, I'll finish.
So next we have some questions. If there's people in the audience here or on Zoom that have questions, you can line up the microphone. I can say that I have so many questions, spending half of my life in Israel and the other half in California, both places with a lot of water issues and different solutions and different policies. So I'll start with one question and hopefully we'll get more from the audience here. I think that everybody has some connection to water. We all drink water, we bathe, we use water. But the way we look about, in my small, personal observation, there's context. For example, in California, you could use treated water for drinking like they use in Singapore, but we don't. In Israel, all of the water is reused pretty much for agriculture or other uses, and we don't have pipes with treated water going into the ocean. But the whole idea, which brings us back to education, is a lot about perception, a lot about what people think, value, what they know. What would you communicate or say or talk to people in terms of finding solution to solve some of these scarcity or temporarily or a scarcity, seasonal scarcity, solutions, for example, about reusing and recycling water or desalination or things that are available but people reject because of preconceived ideas. You can take turns.
Yeah.
So I think this is a great question that I definitely don't have the answers to. Otherwise, I'd be rich and famous and doing something else. I think what's really exciting, actually, when we think about water use is that there is this personal connection to water that in a lot of ways people do understand how they use water and how they're connected to water. And it turns out that our water footprint, for the most part, isn't actually about liquid water, not the way we think about it. Our water footprint is embodied in the food we eat. It's embodied in the electricity in our homes. It's embodied in the stuff that we buy. And that's all things that aren't wet. And what I'm really intrigued by is actually getting away from my beloved water and hydrology roots and inspiring people to think about what the end goal is and how we can get there differently. So as a hydrologist, I tend to think about efficiency, like, ooh, can we use the water better? But what if we just take a completely different approach to things? So my favorite example of this is Peruvian, I think, the chinchilla. The chinchilla needs to be clean, but it takes dust baths. Okay, if what the point is that you need to not be oily, are there other ways to not be oily than to wash with water? Well, dust baths. What are we trying to do? What are the endpoints? And are there ways that we can get there that aren't water related or aren't as water intensive at all? And those are the kinds of innovative things I'm excited about seeing a new generation of out-of-the-box thinkers come up with.
Oh, I was just going to say, shout out to Israel. Yeah, a lot of the irrigators in Eastern Oregon are now using technologies from Israel because they are so advanced in their irrigation. I hate to say it, but I've worked in water for a while. I'm young, but I've worked in water for a while. And moving to the West, desperation makes people think creatively, unfortunately. I was hired with someone with the same position who works in irrigation. And it's been interesting traveling around with her because when people mention water quantity, they immediately perk up because it affects them. When you mention water quality, then people get scared because we live in a climate where things are just so political. And so trying to think creatively and trying to make that resonate for people and trying to find the importance. I also don't have the answers on how to do that, but I think it's easier to do in areas where you have to. The situation necessitates thinking creatively.
Yeah, I agree. I think, you know, the Southwest right now with the Colorado River is facing that challenge. You know, the river has about 50% less water than we thought it had, at least currently. So people have to innovate. You know, they have to find ways to use water more efficiently, using drip technologies, using technologies like that. But something Kate said made me remember, right? Most of the time when we think about problems with water, we don't actually, it's not actually the water itself that we care about. It's the ecosystem, it's health, it's the food, and if we can, or it's cleanliness. And if we can find ways to get those things using less water, you know, the classic, you know, early on in California when they started having water problems, they told people to stop hosing the sidewalk off with water, maybe use a broom instead. I mean, sometimes if water's been plentiful, you don't think about it, but if it's scarce, you go, okay, we can find other ways to accomplish that task. But I think the focus is what you want are healthy ecosystems. Sometimes it takes a lot of water, sometimes it doesn't take a lot. If you want food, maybe we can find ways to be more efficient. So efficiency is certainly part of it. When I talk to people about domestic water use, they're always asking about appliances and toilets and showers, and those are all well and good. But as noted, right, all that water goes to the treatment plant and potentially can be reused. I always tell people, look, it's all the water you use outside. That's the cost. And farmers don't have a choice. If they want to grow food, they need to irrigate the crops. And irrigated agriculture, there's a reason people have irrigated crops for, well, 10,000 or so years at least. And that's because it works very well. It produces a large agricultural excess. But it's that water use outside, particularly for domestic and municipal purposes, where there's a lot of low-hanging fruit, where people can still have the aesthetically pleasing places to live, but not the cost of the water.
Getting rid of that ick factor. I'm not exactly sure how to do that, because treated wastewater is, I mean, you have water, why not treat it? You treat to the level where you can drink, but then you just get rid of it.
Well, but I agree, but then part of it is marketing.
Yeah.
So when you go with a market campaign that says toilet to tap, it's a big no-no, and that's what they did. If you have, I don't know, Brad Pitt drinking water on TV, everybody's going to drink that water.
So in Arizona, and I think this has been done in other places in the Western U.S., they brewed beer with effluent, and that is an effective marketing strategy.
And in Singapore, they call it new water.
Right.
So it's just a matter of, go ahead, sorry, we're hogging.
Oh, no, I was enjoying the conversation, yeah. No, I thank you for all the talks. I thought they were very great. I have questions, I think, for all of you, but maybe just one for now for Dr. Brahman. I thought you did a great job of sort of integrating global water concepts, but also acknowledging that it's local problems, like they're very complex. I'm from Utah in the USA, and I mean, we have these, it's in the news all the time. It's made it to the New York Times, you know, now about our Great Salt Lake dwindling. But one thing that I kind of, the impression I was left with after your talk was that you see this relationship between conflict, water conflict and water scarcity as not always being where we might expect it. But do you think that that is part of the steady state process now? And do you expect that to change as climate change impacts these areas in very different ways? Does that make sense?
Yes. That is also a great question. Another one that if I had a really good answer to, we could take over the world. I actually am not a doom and gloomer about this one. So Aaron Wolf at Oregon State University is like the person to go to who's done really excellent work on transboundary water conflicts. And what he's found and what I've seen in the reading that I've done is that, especially at an international level, that's where we see cooperation. And it happens because there's good institutional strength. Nobody wants to go to war because war is expensive and it's politically bad for you most of the time. And so there's been really interesting ways where water has actually spurred cooperation. So between Israel and Jordan, there's actually been one of the sources of cooperation there has been driven by water and water shortage. Where I think we're more likely to start seeing conflicts and conflicts that could bubble up to being a bigger problem is at the subnational level. And in places where there's not that kind of institutional support to mediate what are in fact real conflicts. But this again comes back to these questions about equity and justice, and also then feelings of unfairness. So, you know, when you actually look at the landscape of where fighting tends to happen, I think Ethiopia is a great example. It's actually not in the really dry places of Ethiopia where you see conflict over, in this case, farms and farmland, because nobody wants to fight over the really crappy farmland. They're fighting over the farmland in the Tigray region, which is better. It's still limited in water. They're still having some major impacts of drought there, but we're also seeing a lot of conflict because people are moving out of the really water scarce areas into the relatively more abundant areas. And then that's where the pressure on water comes from, exacerbated by long-standing ethnic conflicts. And so it's feeding into lack of institutional settings, existing conflict settings, and relative abundance in a setting of scarcity. And so those are actually the places that I worry about more. But this is something that I think there's a huge research gap in. This is one of these many places where good social science research has not been well aligned with good biophysical research. And as a result, there's huge knowledge gaps that actually shouldn't be that hard to fill. And so this is one of the things that I'm getting really excited about studying, and I would love to talk more about it with anybody who wants to. I have no answers.
I'll just follow with that sometimes I get the sense with water problems is that people will think they will be solved. And I guess at this point in my career, I've realized, and I've gotten this from John Fleck at University of New Mexico, right? Water problems aren't solved, they're managed. You manage them, you get a little further, you make some progress, and then the next problem shows up. You know, on the Colorado River, maybe the next problem will be really wet years that threaten to take out our reservoirs again. Who knows? I'm just saying that if in 1995 you told people that Powell would be at 35% storage, people would have looked at you funny. I mean, things can change and change relatively quickly, but I think the key for the people and the decision makers to understand is you're not going to solve these problems. The Klamath will remain a problem for the next 1,000 years, but you will manage it. And people will figure out ways to navigate it. And if you can do that gradually over time, hopefully the social dislocation is minimized, which could be large in the Klamath or the Colorado River Basin. So
I think continuity too, it tends to be that resources and attention is allocated in times of need, and then it's forgotten when that need disappears. Things like drought, money goes towards drought, all of a sudden it rains and it's forgotten. And water problems are long lasting. You can't fix it in a couple years. So making sure you have those resources and that institutional setup across time.
Hi, Dan Lappin with Intergenesis. I have a bit of an abstract, esoteric question for you. So in planetary sciences, scientists study water molecules on asteroids. And they think, where's the origin of life? You know, we've got all these planets out there, there's bits of water, there's ice in the galaxy, etc. And they ponder the concept of the water molecule itself. And so I'm curious, within the slice of discipline that you're studying, to what extent do your students ponder and think about water molecules and use that as an inquiry tool about, let's ask water what the solution is?
I think that's your question.
I mean, so I teach a water chemistry class, and in the first lecture is the structure of the water molecule and why it's critical for the existence of life, why it's critical to its unique properties as a universal solvent. In terms of thinking about using it as a prop to then think about how to solve water problems, I don't know. I mean, I haven't thought in that way.
Okay, well, I'd be curious to talk. You're at University of Arizona, right?
Uh-huh.
Okay, yeah, let's chat. I'm talking to Dante Lorente.
Oh, yeah, no, I know the folks over in Planetary. And
yeah, okay.
I exist more on the applied side of hydrology than some of my colleagues, but my colleague Jen McIntosh and Vic Baker both.
Yes, let's chat.
Yeah, both work with Planetary folks. So.
Yeah, I was just thinking about our first speaker, who I guess in Seattle has gotten a little late, and so he's not here. But if I come back to his worldview and why, or Vi, if I say it properly, you know, in our education systems today, I'm not sure how much we teach our children about the interconnectedness of everything, and more that social science and understanding and caring about each other. And so, as I was just in a session which I could not understand. I'm not a biogeochemist by trade, but the very end presentation was, we can no longer predict Earth's future with natural sciences. We need social sciences because of the human behaviors that you see happening today. And so that resonated with me. So I guess the question is the human element as we think forward of like, how do you build more resilient humans and to caring humans, and kind of inspired from the theme of this whole session as well as our first speaker. So do you have any thoughts about that? Both at the global basin scale and then, you know, as you're working with the K through Gray?
I mean, I think people need to understand the physical principles of water, but yeah, the problems of water are largely problems of people. And a shared resource, how to share that resource, how to allocate it. The physical sciences can offer, John Fleck does a great description of this, right? A shared set of facts. How much water is there? When is it available? When is it, what is the actual volume of the shared resource that could be used? Because if you don't have that common agreement about what could be used, you can't start coming to agreement. But once you have that, you can then start going, okay, here's where I can cut back. Okay, here's where you clearly need that water. And if you will, you're getting back to sort of, you know, Eleanor Ostrom's Nobel Prize winning work on shared resources, which, you know, is model. A lot of her work started with the acequias in New Mexico, where you have a person and a group of people figuring out who needs water today. And the guy with the cherry orchard definitely needs it because his trees are going to die if you don't give it to him. But the guy with the alfalfa field, he can wait a couple days. But if you don't know how much water there is, you can't start having that discussion about who gets how much. So the physical sciences can help, but it is ultimately a people problem. And you need the institutions and those sorts of things. And to that, I defer to people who've thought about that more than I have. So,
I think we definitely need to integrate that, because if the problem has to do with people, the decision-making institutions and governance are the people, and they need to know this physical science, but they also, the fact that, again, in the way we, in academia, research hydrology separately from a governance, from environmental justice, they're even in different schools in some places. That's already a challenge. I think all three of you mentioned that food, energy, and water are all very interlinked, and they're studied separately. Agriculture departments, earth science departments, engineering, and they're related. So I think, you know, to start addressing some of these questions, we really need to break these disciplinary silos and work on challenges.
Well, I'll just very quickly, you know, you're right about the academic, but it's fractured governance as well. I mean, I always joke that there's a hydrologist who works for every single cabinet secretary in the United States. You know, all the cabinet level agencies, they all have hydrologists working in them. Department of Defense, Department of Agriculture, even Department of Commerce, right? There's hydrologists all over the place.
I'd be shocked at how unclear that is. Have you been the hydrologist at DOD?
Well, the Army Corps of Engineers is in DOD.
Yeah, they work for the Army.
But anyway, but my point is that you're right about the academic, but it's also true on the governance side. Like in my own work on stormwater, right? There's flood control agencies, there's drinking water utilities, there's the water quality agencies, there's 10 different local agencies, and so no one wants to solve the problem because each of their parts of the problem is a small part. But
I'll say I didn't even know about socio-environmental research until my postdoc, and like I said, it was out of necessity because I started going down and talking to farmers and realizing I knew nothing about social sciences or how to interview people, and I got myself into a lot of trouble. And I think like this setting in itself is really helpful to bring together. So thank you, Adina, for putting this together. And also like things like NSF and the Succinct program, where it was like I went to a workshop where it was like talking about watershed governance, and it was half social scientists and half physical scientists, and coming together and talking about watersheds and trying to think about creative ways. I mean, I'm in agricultural extension and I never had any background in how to communicate, and my whole job is trying to translate science to the public, but we're not given education and how to effectively do that. And even in like now grants like the NSF, you have to have an extension and outreach component, but it's usually just researchers slapping it on in the end and being like, I had a workshop, I'm cool, right? Like, so, I mean, honestly, and so it's like, you need to give importance to that. And like you said, breaking that divide and having people come together.
Including people that talk about water planets, because we can learn from them.
Yep. So I absolutely agree with all of this. You're never going to hear me argue for keeping the silos in place, but I actually really appreciate your question. And is Ramsey still here, or is he off the phone? Did he?
No, he's teaching. The reason he's not here in person, he's teaching a course in Vancouver.
So I would love to hear his answer to this, because I love your question. And I actually think we need to go way further than what we're talking about here in terms of de-siloing academia, because we need new ways to approach these problems that are not the same as the ways we've used in the past. And I would love to see education that really embraced traditional ways of knowing and other ways of knowing to help us come to those numbers, that we don't have to teach the way we teach, we can teach in a wide variety of ways. And by doing so, we can bring new people into this problem-solving space that have been excluded in the past and can actually get different kinds of answers, different potential solutions. And to me, that's so exciting. So yes, I don't know how to do it. Let's do it.
Well, let's have two last questions. Maybe they have answers too.
Wait, mine's not a question. I just wanted to say, so Kumu Ramsey, since he's not here, I think what he might say is, in Hawaiian perspectives, water and other things in the environment, we don't call it a resource, we call it a source. So for us, it's just that change in mindset of what importance we put on the environment, and that really changes how we interact with the environment, right? Like how we study it, how we utilize it, however you want to phrase it. And a lot of the time we call this a new perspective, but it's actually very old, right? We call it like traditional ecological knowledge, but it's new in academia. And so for me, as a PhD student, while I was doing my research, one of the kupuna that I worked with here, he said that to me. For us, Vai is not a resource, it's a source. And that blew my mind, and that was like, that's now the foundation of what I want to do as a hydrologist. So I just wanted to add that, since Kumu Ramsey is not here, but for that Hawaiian perspective.
Thank you.
Thank you again, too, for this great session. So I wanted to touch on the idea of the branding for the water reuse, because I think the other perspective that I've seen over my career being a water quality person is that there's a big disconnect between the science and then the implementation of those standards. And then the other challenge that we have is also that the science, like PFAS is a great example right now. So we're still trying to understand what the effects are from some of these chemicals, and it'll be years before those get regulated. And so even us, I don't think we would say, yes, we feel really good about drinking this water at this time. So we kind of need to merge those two a little bit more rather than them existing in silos, perhaps, as well. and a lot of standards are compromise standards. So there's a whole discussion that could occur, but I think if we can do a better job of, we get really excited when we find a new compound and say, oh, let's look at this, but it could, harm you. Maybe also branding with like, yes, but the most part it's good, or trying to merge some way of our communication.
Well, and a colleague of mine, Wendell Ela, who's now in Australia, but he was in environmental engineering at U of A for a number of years, he said, look, the drinking water standards we have in the United States, at least, were established based on water, quote unquote, coming from nature, coming from relatively natural systems. When you're talking about taking water from a treatment plant, it's natural in some ways, but it's conceptually and actually physically very different. And so he argued, look, you need different drinking water standards for reusing effluent, at least for drinking water purposes, because of that, because of this. It's not just the ick factor. There's a reason the taboo exists, right? Like there's a deep human taboo about drinking water from where you excrete. And so you have to have different standards. And the American regulatory system is not well built for saying, well, because this water came from somewhere else, we need different standards. I think there's an institutional governance challenge there that's very real.
Yet we do it all the time. If you look at the discharge into rivers, discharge upriver, another city pumps it from the river, treats it, drinks it, discharges downriver.
I mean, Orange County recharges the water and then pumps it back down to the ground.
And maybe I'm a pessimist, but I have a friend with the EPA that her research is PFAS, and she was using a filter, and she's like, do you know what's in your water? And I was like, I'm such a pessimist that at this point, everything's in our water, right? Like, and I think it's all a give and take and a compromise. Like I work with things like biosolids, right? You're looking at nutrients applied, and then you have to worry about PFAS, and it's always something. Like you can't have a perfect solution for everything when you need a quick change in solution. And again, maybe that's everything is a compromise, and it's not going to be perfect.
And with that optimistic note,
Can I?
Yes.
So I don't know what the young lady's name was, but I have a colleague, Michael Kututewa Johnson, who's a Hopi farmer, and a professor now at the University of Arizona. But I remember his dissertation work was on Hopi farming methods, which traditional Western industrial farming methods focus on inputs, what goes in, what comes out. And the Hopi's framework is about soil moisture. How do you conserve soil moisture and maintain it? Because, well, they've been farming in a place for 2,000 years that gets about 300 millimeters of rain. And what motivated him to get a PhD was the USDA's NRCS telling him that, well, we don't know that your farming methods are sustainable, which, again, the Hopi have been farming this way for thousands of years. And so there's a lot to learn from what we call this traditional ecological knowledge, or as Michael just says, the way we live. And there's a lot to be learned from it that could help meet the water challenges we have.
Okay, since you called on me, my name's Diamond. I guess I just like to plug, since this is very cohesive with what my postdoc is, if anyone in this session is interested, the NCAR, National Center for Atmospheric Research, which Michael is very active in, has a program called the Rising Voices Center for Indigenous and Earth Sciences, and there will be a workshop in September. And a lot of what we talk about is environmental justice, social justice, traditional ways of knowing, which in Hawaii we call ike. We get our ike from our kilo, from our kupuna. And so if anyone would like to participate in that, I'm on the planning committee for the workshop, and it'll be 100% virtual, so you can attend from anywhere around the world. But yeah, a lot of what we do focuses on water, food sovereignty. Part of it is relocation, since a lot of communities with climate change will have to move out of their coastal communities. So yeah, I thought that was a good plug, so thank you.
Oh, you're welcome.
Great, thank you. Let's thank our speakers again. And I will